Good morning. Today we are going to discuss about Internet of Things using cloud computing. The Internet of Things is a vast network of physical objects or things embedded with sensors, software, and technologies that connect and exchange data with other devices and systems over Internet. Every device, such as a phone, laptop, tablet, desktop, TV, microwave oven, fan, door, bulb, fridge, and different parts of the human body, is capable of connecting to the internet by embedding sensors into them and making them smart devices. The figure shows the block diagram of the working of Internet of Things. Devices like AC, gas cylinder, door having sensors are called smart devices. These sensors collect data and the data is stored in a central database over internet or in the cloud. The data that is stored in the cloud is processed and analyzed and will be used to monitor or control the devices. For example, AC can be switched on or off using IoT. We can lock or unlock door using IoT. We can control the supply of gas using IoT. Figure shows the Internet of Things connected to the cloud and the user interface. Let me explain about cloud computing and how cloud is used in the Internet of Things. Cloud computing is the delivery of computing services over internet or cloud. The services includes servers, storage, database, networking, software, and analytics. Users can access these services whenever they need them. Cloud computing eliminates the need to manage or to maintain any physical infrastructure. Internet of Things is a network of real world objects such as furniture, vehicles, and home appliances which are fitted with sensors, software, and interconnected with other systems via internet and they can exchange data. IoT and cloud computing are closely related because the cloud offers the platform and infrastructure needed to manage and analyze the enormous amounts of data produced by IoT devices. The data collected by IoT devices is stored in cloud and processed, analyzed to control or monitor devices or to use in some applications. For instance, in an IoT enabled smart home where it contains many devices connected with sensors such as appliances, lights, fans, security cameras, thermostats, doorbells, door locks, and voice assistants. All these sensors they continuously collect data and stores the data in cloud. The data stored in cloud is analyzed and processed will be used to monitor or to control the devices or appliances. Major components of IoT. The following are the major components of IoT using cloud computing. They are smart devices, gateway, cloud, analytics, user interface. The devices having sensors collects data. The data that is collected from the devices is converted into compatible format and will be stored in a database in the cloud through the gateway. The data stored in database is processed and analyzed. With the help of the processed data, user may control the devices using user interface. Let me explain about these components one by one in detail. Smart devices and sensors, that is device connectivity. Devices and sensors are the components of the device connectivity layer. These smart sensors are continuously collecting data from the environment and transmitting the information into the next layer. Nowadays, A wide range of smart sensors are available for various applications. The common sensors are temperature sensors and thermostats, pressure sensors, humidity sensors, light intensity detectors, moisture sensors, proximity detection sensors, RFID tags, etc. Gateway. Smart devices continuously collect lot of data. The collected data has to be stored in cloud database. An IoT gateway acts as crucial centralized bridge between local IoT devices, that is sensors or actuators, and the cloud, managing data flow, protocol transmission, and security. It aggregates, processes, and filters data at the edge to reduce bandwidth cost and latency, while enabling security, bidirectional communication between devices and central systems. Figure shows IoT gateway, Raspberry Pi, and Arduino Uno is used as gateway. Sensors collects data. The collected data is pre-processed, converted into compatible format to transmit to the next level. Cloud. Cloud computing. The Internet of Things creates massive data from devices. The data that is generated by smart devices will be stored in cloud databases. The cloud acts as central backbone for IoT, providing scalable storage, processing power, and analytics for vast data generated by the devices. It enables real-time monitoring, remote device management, enhanced security, and cost-effective on-demand infrastructure. Apart from storing data, the cloud analyzes the data using artificial intelligence and machine learning models for insights, for monitoring and controlling of devices. For example, traffic management in smart cities using IoT, smart agriculture, and manufacturing. Analytics. Cloud system integrates billions of devices, sensors, gateways, protocols, and data. Cloud provides predictive analysis on the data that is stored. IoT analytics involves processing and analyzing vast heterogeneous data streams from connected devices to uncover actionable insights. It transforms raw sensor data into meaningful patterns, enabling predictive maintenance, real time monitoring, and optimized operations. Main functions of analytics is to enhance data processing, interpretation, real time monitoring, decision making, predictive maintenance, optimization, and improving efficiency. Analytics helps in understanding customer behavior and market trends, leading to the development of new products, services, and revenue streams. For example, the analyzed data is used in applications like smart cities, agriculture, and manufacturing. In smart cities, the data related to traffic patterns are analyzed to reduce traffic congestion. In smart agriculture, the data related to soil moisture, crop health, and livestock health will be monitored to optimize the resources. In manufacturing, the data analysis is used to enhance the operational efficiency and equipment reliability. User interface. User interface in IoT enable users to monitor, control, and interact with connected devices through GUIs, voice, or gestures. Common examples include smartphone applications like Q Ring, web dashboards for data visualization like smart thermostats, smart speaker interfaces like Alexa, and physical panels on smart appliances. Examples of IoT user interfaces. First one, mobile applications. Most common UI allowing users to control devices like smart lights, thermostats, and security cameras remotely. For example, Philips Hue app used to control lights and Ring app is used to control doorbells. Voice controlled interfaces. Systems like Amazon Echo, like Alexa or Google Home, are used to control IoT devices using voice commands. Web dashboards. Industrial and consumer IoT often used web based dashboards to display real time data visualizations, graphs, and trends for energy consumption or manufacturing metrics. Physical hardware or on device interfaces. Smart appliances and gadgets like smartwatches, washing machines often have built in screens or, in some cases, gesture recognition technology to interpret physical movement. Wearable interfaces, smartwatches, and trackers such as Fitbit provide concise data visualizations and health insights directly on the wrist. Architecture of IoT. The architecture of Internet of Things consists of four different layers: sensing layer, network layer, data processing layer, and application layer. Sensing layer gathers data. Network layer transmits data to store in database in a cloud. Data processing layer processes data and analyzes data. Application layer is used data analytics in a smart application. Let me explain the layers one by one. The first one is sensing layer. This is the bottommost layer responsible for detecting physical conditions from the environment. The functions of sensing layer are collecting raw data such as temperature, humidity, motion, sound, or pressure. Senses changes in surroundings through embedded components. Initiates actions using actuators when required. Components that are used in sensing layer are sensors like humidity, gas, infrared, ultrasonic, actuators like motors, switches, valves, microcontrollers, and RFID tags. Communication. The sensing layer transfers sensed data to the network layer via wired or wireless links. The second layer is network layer. This layer provides connectivity and communication between IoT devices and cloud systems. Functions of network layer are transmitting collected sensor data to store in cloud database for processing. Supports device to device and device to server communication. Handles addressing, routing, and data forwarding. Technologies that are used in network layer are Wi-Fi, Bluetooth, Zigbee, LoRaWAN, Ethernet, and satellite networks, supporting devices, routers, and switches. Data processing layer. The data processing layer analyzes, filters, and interprets data received from network devices. Functions of data processing layer are cleans and formats raw sensor data from meaningful insights, applies analytics to detect patterns or abnormalities, stores data for historical analysis or reporting. Components used in data processing layer are IoT cloud platforms, data lakes, warehouses, stream processing, and machine learning engines. Output of data processing layer are predictive alerts and reports, anomaly detection signals, decision rules for automation. Next is application layer. The application layer is the topmost layer which interacts directly with end users and business systems. Functions of application layer are it provides interfaces to monitor, and control IoT devices remotely, displays visual analytics through dashboards and charts, triggers automated actions based on processed insights, components that are used in application layer, mobile applications, web dashboards and portals, visualization and alerting tools. Capabilities of application layer are remote device management, real-time condition monitoring, integration with enterprise applications. Applications of IoT using cloud. Some applications of IoT are smart agriculture, asset tracking, smart grids, home automation, industrial automation. Let me explain one by one. Smart agriculture automates irrigation schedules, monitor soil conditions, and analyzes crop health using real-time sensor readings. Next one is asset tracking. Monitors the movement of vehicles, shipments, and equipment using GPS, telemetry, and beacon signals. Smart grids balances power distribution, forecasts consumption patterns, and reduces transmission losses dynamically. Home automation controls lighting, door locks, appliances, and climate settings based on user behavior patterns. Industrial automation predicts machinery faults, schedules maintenance, and improves production accuracy in factories. Advantages. Some advantages of IoT architecture are scalability, resource efficiency, real time insights, interoperability, predictive analytics. Let me explain the advantages one by one. Scalability supports the integration of additional devices and sensors as business requirements grow without major architectural redesigns. Resource efficiency. It minimizes power consumption and maintenance overhead by optimizing operations through data driven control. Next is real time insights. It provides instant visibility of ongoing processes using live sensor streams to enable faster responses. Interoperability allows cross vendor device communication through open protocols to improve connectivity in diverse environments. Predictive analytics forecasts equipment failures and workload functionalities using AI models to reduce unexpected downtime. Next is disadvantages of IoT. Some disadvantages are security vulnerabilities, high initial costs, compatibility challenges, network dependency, complex maintenance. Let me explain the disadvantages one by one. First one is security vulnerabilities. Connected devices are susceptible to cyber attacks, unauthorized access, and data breaches due to weak security layers. Second one is high initial costs. Implementing sensors, gateways, and communication infrastructure requires significant upfront investment. Third one is compatibility challenges. Different vendor standards and communication protocols create difficulties in integrating heterogeneous systems. Fourth one is network dependency. Connectivity issues can interrupt data flow and disrupt real-time operations across remote deployments. Fifth one is complex maintenance. Large-scale IoT deployments require continuous monitoring, regular updates, and specialized management tools. What is edge computing? Edge computing refers to the deployment of computing and storage resources at the location where data is produced. The computation takes place at the edge of device network, which is known as edge computing. That means a computer is connected with the network of the device which processes the data and sends the data to the cloud in real time. That computer is known as edge computer or edge node. With this technology, the data is produced and transmitted to the devices instantly. Yet, edge nodes transmit all the data captured or gathered by the device regardless of the importance of the data. For example, in the Tesla self driving car, the sensors constantly monitor the area around the car. If it detects an obstacle or pedestrian on its way, then the car must be stopped or move around without hitting. When an obstacle is on its way, the data sent through the sensor must be processed quickly and help the car to detect before it hits. A little delay in detection could be a major issue. To overcome such challenges, edge computing and fog computing are introduced. Applications of edge computing. Edge computing for manufacturing, edge computing for farming, edge computing for better healthcare, edge computing for autonomous vehicles. Fog computing. Fog computing is an extension of cloud computing. It is a layer in between edge and the cloud. When edge computers send huge amounts of data to the cloud, fog nodes receive the data and analyzes what is important. Then the fog nodes transfer the important data to the cloud to be stored and delete the unimportant data or keep them with themselves for further analysis. In this way, the fog computing saves a lot of space in the cloud and transfers important data quickly. Figure shows the architecture of fog computing.